again, we are on information video notes for Monday, the 16th. We're going to cover notes 30 through 40. So we left off on our last session looking at some practical uses of radioactivity, that radiation. And so now we're going to move into our last two parts of this unit. They are dealing with nuclear reaction, so nuclear fission and nuclear fusion. We're going to start with fission. I understand that these two words are very closely related, like they sound alike. It's easy to kind of get them confused. So hopefully I'll be able to give you a few ways to kind of keep them straight. So nuclear fission is the one we're going to start with. Again, please notice that there is a brain pop that goes with this, so make sure you're watching that. There will be a few other videos that are linked for today's information as well, so make sure you're keeping up with those. Again, those are going to be almost as important as what we do here, but they just kind of help solidify this information. So definitely you need both things, what we're doing here and then the videos that are linked with them. So the first nuclear reaction we're going to examine is this idea of fission. Okay, the process of splitting a nucleus. Fission. Two new nuclei with smaller masses are created during this process. The word fission sounds like division. Division is splitting something up, and that's exactly what happens in a fission reaction. You're taking a big, large, unstable nucleus and you're rearranging it. You're splitting it up and you're changing it into new elements because now you have an element with a different number of protons than you started with, and anytime you change the number of protons, you are changing the element that you're dealing with. You've heard me say this probably 50 times already this year. Hopefully it's sinking in. Mostly this is going to happen with elements that have an atomic number of greater than 90, because remember, your atomic number is your number of protons. So if you have 90 protons, you have close to that in neutrons. So your mass is close to like 180 or 200 probably even in some cases. So that's a lot of particles that are sticking together in that nucleus. That's why it's not able to stay stable. Think of that example again of the girl carrying the boxes. She could carry several of them, but when she got too many, they got too far apart and it got uncontrollable. That's what happens with a large nucleus. The nucleus itself is so spread apart that strong nuclear attraction that's keeping the neutrons, or that's keeping the protons from repelling each other, is not able to overcome that repulsion, and it falls apart, right? Because we know that the neutrons serve as that glue that keeps that nucleus together, but if it's spread all around, you're not able to get that continuity or that whole nucleus to stick together anymore. Again, think of like the popcorn balls. You don't make giant popcorn balls, you make them about the size of a baseball or a softball at the biggest, because even the size of a basketball, it's not going to stay together, it's just going to kind of fall apart. Okay, so that's why it's when you have these very large nuclei that this is going to happen. So energy is going to get released during this reaction, and it can be used for electricity or nuclear weapons. Those are the two main ways. The Bill Nye that we started this unit with was all about, using it for power, right, for electricity. We will look just a little bit. I know people get really excited about the nuclear weapons part. If you're curious, if you want to do a little bit of research and look into that a little bit more on your own, we could spend, a month just on nuclear weapons. So I know that sometimes we introduce things and then we don't get to follow through a whole lot with them. So if it's something that's really interesting to you, which it tends to be for a handful of people usually, look into it more and then let me know what you find out. Okay, so we're going to just look at the basics of what's going on. I'm not going to need you to tell me exactly what's going on, just as long as you have kind of a general idea or knowledge. I should have deleted this, so it's going to kind of cover up my type here in a minute. But a chain reaction is going to be an ongoing series of fission reactions, because when you start one, it's kind of like dominoes. You have a fission reaction, and then it kicks another neutron, and then it hits into another big nuclei, and then it releases some neutrons, and those neutrons then hit into more large nuclei. So this can become an exponentially huge reaction very, very quickly. And this is the basis or the foundation behind how nuclear power plants work. And we'll look at that. We saw it in the Bill Nye, and we'll also see it a little bit more on a few of these other videos. Again, think of playing dominoes, the game, not the pizza, right? The little white dominoes. If you set those up, you can get them to kind of hit into each other and keep falling. So nuclear fission occurs when scientists bombard a large isotope with a neutron. Seems easy enough, right? Think of it kind of like if you're playing pool, when you rack the balls and you hit the cue ball into that racked triangle, right? It's going to scatter them. Well, it's kind of that idea, except the nucleus doesn't like just burst and go into a bunch of different pieces, like the balls get spread everywhere on the table, but you're going to get a splitting or a division of that large nucleus. And this collision causes the large isotope to break into 2 or more elements. But again, it's not going to go into like 5 or 6 or a bunch. It's going to go to maybe 3, is pretty typical. This releases a massive amount of energy. And you can calculate the amount of energy produced during a nuclear reaction from Albert Einstein's famous equation, E equals mc squared, where E is energy, m is mass, and c squared is the speed of light. So how much energy is based on the mass and then multiplied by the speed of light squared. So here's a neutron, here's a large isotope. The neutron hits that, and it's basically like carrying the boxes, and if you add one more, it does you in, right? And they go tumbling. That's kind of what happens. It gets it to the point where it's just too big, and it will split. This is showing our little cartoon version of energy, right? And then you get 2 new nuclei because you have protons and neutrons here, but then 3 neutrons are released. Those neutrons are now available to hit into their own large nuclei, and this is where the chain reaction part will come in. You can see it down here as well. 1 neutron hitting into this uranium-235 isotope, it does it in. It's 1 too many, and it just causes it to split. So you see it kind of split apart, and you get 2 smaller nuclei that are formed, and it releases 3 neutrons in the process. And then those 3 neutrons can act like this one and continue the process over and over. So you can see this going on and on. So this is the chain reaction. The uranium is the blue, and as long as there's uranium, if there's neutrons there that can bombard it, it will cause those uraniums to continue to split and split and split until it runs out of uranium. So the nuclear reactions of a power plant basically work on this concept, right? So here's a picture of the United States, the blue dots, or triangles, excuse me. The red circles represent the area that could be affected if there was some kind of nuclear accident. So you can see, here's the nuclear power plants, and then look at the mass, right? We're kind of in a danger zone if we would have any kind of major nuclear accident. We will look at the main one that we've had here in the United States was back in the 70s, and it was 3 Mile Island in Pennsylvania. We'll watch a video on that on another day, so I'm not going to go into that too much right now. You'll get that in the notes, or excuse me, in the video. These are the notes. So I just kind of like to show that picture of here, in the United States. Again, notice that there's a brain pop video here, so if you make sure you watch that, it is linked in Google Classroom. So back to the reaction though, if the neutrons can be controlled, then the energy can be released in a way that's controllable, and it becomes very, very useful. Nuclear power plants produce heat through these controlled nuclear fission chain reactions, right? And it's that heat that then produces steam and then generates gets the turbines turning in the generators, and that's how we get the electricity that's produced. So we're going to kind of go just briefly into the setup of these nuclear power plants. Again, I'm not going to need you to know the details or tell me, oh, this happens, then this happens, and this happens. I just want you to have a general understanding, because again, this is an important topic for your future. It might be how we're getting all of our power in the next 20 or 30 years, right? So it's good to kind of have a basic foundation and understanding. So the fissionable isotope is held in these things called fuel rods in a reactor core. The control rods commonly are made of boron and cadmium, and they are in the core, and they kind of act like neutron sponges, because if every time fission occurs and a uranium splits, you get 3 neutrons that are produced or released. You don't want just neutrons out there available to bombard all of the uranium. So what happens is, if they can kind of attract some of those neutrons, you can control the level of reactions that are happening, and it doesn't become this uncontrollable chain reaction that becomes out of control and deadly. Okay. So here's a picture, and I know it's probably a little bit hard for you to see, so I'm not going to spend a ton of time, but in the nuclear reactors, the heat is generated by the reaction, and it's used to produce steam that then turns the turbines, and inside the turbines, they're connected to a generator, and that generator then converts that nuclear power, basically, to mechanical, and then finally into electrical energy. Kind of an up-close view. Here's the fuel rods that contain the uranium. There is cooling fluid, because this all produces so much heat, you don't want things to melt and cause a meltdown. You also have the control rods. In the control rods, that's where you typically have the boron and the cadmium, and they're able to absorb some of those neutrons and control the number of neutrons that are available to cause the uranium to split in that fission process. So the reaction is kept in check by the control rods, and these block the pass of the neutrons, keeping the system from reaching that dangerous supercritical mass where you have too many reactions taking place all at once. Okay, so in the US there are approximately 100 nuclear reactors, and we saw that on that map. They're only producing about 20% of our country's electricity, and I did just look up these numbers again to make sure that they hadn't changed, because I told you it had been a few years since we've done this unit, and it's still where we're at. So the advantage is that there are no fossil fuels, meaning those non-renewable resources. We're not burning coal. Also, no combustion reactions, so we're not getting any of our typical pollutants that we get when we're burning those fossil fuels. It's pretty inexpensive to operate. Once you get the plant up and running, it's pretty cheap to operate. To get it built, it's expensive, but the actual day-to-day is pretty inexpensive. So some disadvantages: it is expensive to build. And sometimes there can be a limited supply of that fissionable uranium-235. So again, the uranium-235, kind of like coal, it might get to a point where it might be hard to find that is in good usable form. There can be accidents, and again, I'll leave that for the videos for another day. 3 Mile Island and Chernobyl. And then the disposal, and this is what the Bill Nye video focused on a lot. The disposal is very expensive. What are you going to do with it? They talked about sending it to space. They talked about burying it out in the desert. There's a lot of options. They're still trying to explore and figure out what is going to be best. Okay, so again, this is a hot topic subject. So these are the videos that you're going to watch next for you, whatever day that might be. They will be posted for Tuesday the 17th. Again, make sure you're going in the order that things are, day-wise. So do Monday the 16th, then Tuesday the 17th, then Wednesday the 18th, and that kind of thing. Again, I'm not going to expect you to be able to tell me the exact steps in the process of a nuclear power plant. I just wanted you to be aware of it. With fission, you definitely need to know that it is a division. It is a splitting of a nucleus. So a large nucleus becoming two smaller nuclei. Okay, that's kind of the key for today. I hope you guys are doing well, and I will be checking in with you soon. Take care.